Because when we talk about use of computers in manufacturing, and certainly the controllers, as I was mentioning, that we are also concerned about the embedded controllers and the industrial controllers that are being used for controlling various equipments, and that is also an integral part of the smart manufacturing and computer-aided manufacturing. Whether we talk about the controller of a CNC machine, whether we talk about the controller of a robot, or a similar system, we always have to understand the basics of the numerical control, and before that we need to understand the basic industrial controllers, that is the programmable logic controllers. So we will be starting discussion on the PLC today, and at least I will give you some input and understanding on what exactly the PLC is and how to do a basic programming on that. And then subsequently in today's lab, you will be able to get some experience of doing a programming on it. So when we talk about the CNC, actually, that is the numerical control system, and especially it's in a computer numerical control these days. There are three types of software programs that we need to understand in the CNC. So when we talk about the software programs, now you all understand the CNC part program, actually. That is what I'm sure that. So this part you are familiar with, this NC part program part you are familiar with, because when we talk about the CNC programming, you all get to understand what is the NC part program. But if you look at this, NC part program is kind of an application that you want to run. For example, for a particular machining application, or maybe for 3D printing, or maybe for CMM, maybe to control a robot. These are the user application that you will be running. So you will be giving an input in the form of an NC part program to your system. But that is not the program which is running inside the machine controller. So we need to understand that aspect. When we are talking about the CNC software and the programming CNC, we will be trying to understand the programming CNC controller, not the application program alone. So we will be discussing that part also. So we will be discussing CNC part programming also. But before that, we will be discussing the machine interface software and the operating system software of a CNC machine. So I'm sure that all of you have seen CNC machine somewhere, and if you look at this, you will be entering some part program into the machine controller. Now, if I write a simple instruction of, as I was mentioning, N10 X15, now how this program will get executed. So how the machine will understand this program, and then once it understands that you want to give a displacement in the X direction 15 units, and most of the time these units are millimeter or inches. In that case, how the machine controller will execute that motion. So that is an important part to understand. Whenever you are giving M code M03 or M04, now once this statement comes in your part program, how the machine controller should act and what is the actual hardware and the software that is making it happen. So that is the part we need to understand. I'm sure that you might not have gone into that much depth. You might have understood some part of the CNC part programming, but that is what we are trying to cover up in this course. So when we talk about the machine interface software, basically, this software is basically used to communicate between the machine tool and the computer that you have. So computer, when I'm saying computer, it's basically the HMI, that is the human machine interface. So there's a computer interface through which an operator will be interacting with the machine, and then there's a machine tool actually. Now how these two will be coordinating the functions. So in the machine tool, you will be having the different axes of motion, and you are also having a different elements to be controlled. For example, if you want to do the coolant on, coolant off, or you want to do maybe the tool change operations. So there are some automation functions in the machine, and there are some motion control functions into the machine. Now, to execute these functions onto the machine tool, your computer has to issue a necessary command, and there has to be a necessary hardware on the machine tool, which will be controlling these motions and the logical control part. So most of the time this machine interface software we will be writing in the ladder logic programming, and that is what we are going to discuss now. I just want to give you a reference and the relevance of this PLC programming, how exactly it has been used. So we will be starting with the understanding of a basic logic operations, and then we will be subsequently discussing how the motion control will be implemented on top of that. Then apart from that, there has to be a operating system software into the CNC machine. Now this is something which is making an interface between a user and the computer into the computer hardware under the machine tool. And there we will be writing some program. So if you understand that there's an application need that you will be writing in a part program with the alphanumeric instructions, then these instructions will be understood by this operating system software. There has to be some software application which will interpret the part program. So this parsing of these instructions, whether it is an X10 or X15, and then what is the displacement in Y direction, what should be the spindle speed, all this parsing will be done by operating system software. So it has to interpret the NC part program and then generate the control signal so that it will command the machine tool access. It will also have a provision that you should be able to edit and write the part program. So that kind of file management is possible. So there's an editor application as part of the operating system software. And then there's a control program which will decode the part program instructions, do the interpolations, calculate the acceleration, decelerations, and then these are related to the motion control applications. And then do the axis coordination, because whenever you are implementing the interpolations, how that coordination will happen. So all sort of computing will be done by this operating system software. So you understand the three main elements of the software that are operating in any of the CNC system or the numerical control system. One is certainly the application software, where the user will be writing what exact motion he wants to have. Then this program is interpreted by the operating system software, which will further commanding to the machine controller. And this so there could be two controller. One is the logic controller. There could be a motion controller, or they will be combined together into one single controller, because these days the industrial controllers are available which can handle the logic control as well as the motion control in single hardware. Earlier there were two different, so logic is being implemented in the logic controller, that is the PLCs, and the motion controller is implemented into the motion controller, which are being added separately into the machine tool. So that is the broad understanding of these the software programs. Slowly we will be understanding one by one. So we will be starting understanding with the logic program, and then we will go to the motion control part, and then we'll talk about the CNC part program. So that is how we will be covering in this course. Now, when you look at this CNC auxiliary functions that I was mentioning, that the logic control, when we talk about the PLC, it's a programmable logic control. So we will be writing the logical instructions that we will be discussing. So if you can see the kind of a logic control functions being required in the CNC machines are basically the coolant control, that is on and off you want to do from the PLC. You will be controlling the pump that will be flooding the coolant into the machine. There will be the automation which will be doing the fixture clamping. So there are fixture clamping devices. So unclamp and clamp the fixtures there. You have an emergency warning and a stop. These inputs will be going into the machine. So there are some push buttons on the machine, and these push button inputs are going somewhere into the controller inside. And accordingly, you will be identifying what all action will be taken up by the machine when you press some buttons. So these buttons are basically forming a part of the input to the PLC. Then you have a part loading unloading arrangement. So where there's a sequence implementation with interlocks. Then you'll also be counting the parts. So there are certain counters which will be counting the parts being produced. So these are some of the control functions being implemented into the CNC machine. And most of these functions are done with the M code actually. So if you understand the G and M code of a CNC part programming, you will be able to understand Now, with this understanding of this PLC programming, you can understand how the machine will execute the M codes. So if I write M03, how this instruction being physically controlled, or how this will physically control the machine hardware. So that part we will be understanding through the PLC programming. So earlier, people were doing this logical implementation with the help of a relay logic circuits, which we are not discussing, because normally when we do the automation course, we'll cover up the basics of the relay logic circuits. But we are directly jumping onto the PLC programming in this course. Most of the logic being constructed with the help of an electromagnetic relays, which are now obsolete, and we are implementing directly into the programmable way in the PLCs. So let's talk about what is PLC. So as I was explaining, it is a programmable logic controller. That is how the abbreviation stands for, and it is an industrial computer. It's almost similar to all sort of computing system that you're familiar, whether it's an embedded controller, whether it's your main PCs or the servers. Everyone is having basically the CPU and the memory to execute the digital program. So these are the digital controllers. All instruction processing happens in the digital format only. And then we are using them for monitoring and control of the industrial processes. So there is no system without PLC today. So all of the industrial machines, whether it's a CNC, whether it's an assembly line, whether it's in a robots, all industrial control systems are having some form of these PLCs inside them. And the idea is that we will be monitoring some of the parameters in the process, and then it will also be able to control the industrial processes. So that is the main functionality for the PLCs. And they are easy to program, because if you see that the way we will be learning programming, this will be in a graphical programming. There are many programming languages in which you can program these industrial controllers, but the easier one or the easiest one is the graphical programming, and which we call the ladder logic. So we need to understand there are a few more programming which we may not be covering them completely, but we'll get an idea what are those programming languages. Only programming that we will be learning is the ladder logic. And then based on the requirements, they are available in various form factors basically, and there are various arrangements. So we'll just have a quick glance on that. And they will be operating at different voltages, but the most common one that we are using in industry is operating at the 24-volt DC. Rest are not relevant. So we need to provide an additional power supply to them. Now, there are many manufacturers of PLCs. So some of you may heard about them. The Siemens, Fanuc, Omron, Allen Bradley, that is the Rockwell automation. So we will be using the Rockwell automation, that is Allen Bradley PLCs for our labs. That is how you have got those softwares, the RS logics and RS links basically to communicate with the, because with the Rockwell PLC, because in our lab we have physically these Rockwell PLCs. And once you learn any of the PLC environment, most of the PLC environments are similar, and there are certain standards to be followed by the manufacturer. So if you want to program Siemens PLC, once you understand the Rockwell PLC, you need not to learn everything from afresh. You already get familiar with, only the user interface will be little different, and then you can learn that. Now, benefits I will just run through. We're not going into too much details on that. As you understand, it's in a programmable, so that you will be able to control the functions. So these benefits are explained with respect to the relay logic actually. And the relay logic is mostly the hardwired system. So you will be making electrical circuits, and then you will be making the logics to operate. And once after the advent of the PLCs, then you will be writing all the logic in the software form, and then it is reprogrammable. You can erase the logic and then you can build it again. Your physical interface will remain same. So that is the advantages of the PLCs over the hardwired logic done with the relay circuits. Now, broadly, if I will explain you what exactly the PLC, the architecture part. So let me just explain you this. So as it is a digital controller, so most of the digital controllers will have CPU, that is central processing unit inside it. So inside the core of the PLC, there will be a complete computing system, that is with a processor with the read access memory, random access memory, as well as the ROM here. So ROM we are not using these days. It's a flash memory, so which is responsible for storing the program that you will be writing into the PLC. So we will build a logical program and then we will transfer that program into the PLC memory, so that this programmable logic where you will be writing the logic and you will be transferring that binary code into the PLC core. So CPU will be reading those programmable instructions and it will be executing the logic that you have written. But this industrial controller, because your devices that you are using today, whether it's in a PC or the laptop or your mobile phone these days, all are having the same core inside it. So there's an 8-bit, 16-bit, 32-bit or 64-bit controller inside it. And then there's a memory interface to that controller. So you will be having a RAM into your system. You will be having a hard disk or maybe a SSD or a flash memory inside the system that will be storing the data even when the power is not on. So these are the memory interfaces, and then CPU will be executing the program as you want to have it possible based on how you will be interacting with the system. Now, when we talk about the PLCs or the industrial control systems, you need to physically interface some of the devices here. So normally when we do the mobile phone, there are some interfaces available, but rarely we connect anything physically to the device. Most of them are wirelessly communicating, and you have only the USB interface these days so that you can exchange some data with the controller. Same is with your laptop and desktops. You have certain ports available onto the system. Some of them are the display port, the USB port, LAN port. So these are the kind of interfaces you will find on your desktop or the laptops. But when we talk about the industrial controllers, the PLCs, we need to have interface where we can connect the sensors, where we can connect the actuators, because that is the basic idea of having this controller on a machine, that they will be either making some systems on and off and they will be sensing some of the parameters. So PLCs, if you see here, apart from the basic architecture of a computing system in the core, you will be having an input module and you will be having an output module. It means that I will be having certain physical terminals over here, and on these terminals I will be able to connect the input devices here. So there are some input signals that I will be interfacing on the left hand side. And on the other side, then when I'm saying left hand side, right hand side, they may be spread differently in the actual hardware, but there are the input interfaces and there are output interfaces. So on output module, you will be interfacing the devices which will be used for control applications. So whether you want to extend an actuator or whether you want to make the motor on and off, all these functionalities done with the help of an output module. So on one side you have an input signal coming in, and other side you will have an output signal going out from here. And how these two are linked together, that is through the program, how you want to react to the input that is coming inside the PLC. So that part you will be writing in the form of a logic here. So you will be writing a logic inside it. Logic is basically connecting the input signals to the output signals. So how your output signal should behave when there is an input signal is available. For example, if there's a fire sensor I have connected to one of the inputs to the PLC, and then I would like to just indicate that with a hooter. So you would like to make a hooter on, or you would like to take some action so that you want to make the gas flow inside the chamber, or you would like to make the water spray to happen. So there are many ways in which you want to control the fire. Now, based on this input signal, whenever it is available, you want to do some action, and these actions are executed with the help of an interface to the output module. So you have an input signal for sensing, you have an output module for actuation, and in between resides the logic here. So that is the three important elements of a PLC. If you understand that, I think then you will understand fairly the PLC hardware. and then we will understand how to interface the different sensors and actuators over here, and then write the program. I'm sure that you understand this basic module. I just made it as simple as possible so that you will understand there's a controlling on the CPU unit in between, and then you have on one side an input signal, on one side is an output signal. Now, most important part when we discuss PLC is the hardware that we need to understand. Which hardware should be connected to the input side and which hardware will be connected or which device will be connected on the output side. For example, if I ask you where I will be connecting a push button, can you tell where I should connect the push button? Anyone in the class?
Sir, input.
Input side, good. And if I have to control a actuator and I have to operate a direction control valve, where I will be connecting that part?
Output.
Output side, obviously. So that is good. You understand fairly little bit of that part, and we will just again brush up those fundamentals so that we'll understand how we will be using this PLC in the machines as well. So basic components, if you look at the PLC system, you will be having the PLC processor and the controller, as I was explaining to you. Then to this processor and controller, we have these IO modules. That is very important to understand. And these IO modules, as I was explaining, input output modules. So on one side you have input module, other side output modules. And there we have further classification to understand what type of input is coming and what type of output we are going to generate. So we call them AI and AO, that is analog input and analog output. So this is the analog input and output. And then we have another type that is a digital input and output actually. So depending on the type of variable that you will be reading, you will be having these analog inputs and analog outputs and digital inputs and digital outputs. So I will explain them as we go along. If you understand them, it's good. Otherwise, I will be explaining what are these analog and what are the digital means. So we have these four type of modules. Two are the analog and two are the digital. And so two are the input types and two are the output types. So these are the modules that will be connected with the PLC, and they are part of the controller or they may be available in the separate modules also. Then once they are available in the separate modules, we have some chases and the backplane to connect them together that I will explain to you. And to power the whole system, you need a power supply in the system. And then you will be using some kind of a programming environment, which you will learn today. That is what the RS Logics programming environment, where you will be building the logic over here. And finally, you will be transferring this binary to the controller. And most of the controller these days have a connectivity. So we have a network interface. So all are connected on the LAN or Ethernet interface so that we will be able to communicate with the other PLCs. And this communication is a very important part of the smart manufacturing implementation. So connectivity is very important. They are no more the standalone systems today. Most of the machines or the PLCs are all connected inside the plant. So we'll learn that also. So the controller or the processor, as I was explaining, what is the main function of this processor controller? It has to store the control program and the data in its memory. It read the status of the connected input devices, it execute the control program, and finally it commands the output basically based on the program execution. So these are the main functionalities of the CPU that it will be doing. And they are coming in the various form factors, as I was explaining. They are available in the modular form, and they are also coming as an integrated single unit hardware. So let's quickly try to understand the input output module. That is a very important part of the PLC. And because once you understand what are these input output modules and what kind of devices can be interfaced to these input output modules, then we'll talk about the programming that part. Now, most of the controllers or the CPUs or the processors, they used to operate at a very low voltage and the low current. And that is how we are able to run the instructions at a few gigahertz actually without consuming a lot of power. Otherwise, the basic logic execution inside the CPU will take its own power consumption that will be very high. So the core voltages of the PLC are in the order of, or the CPU are in the order of 3.3 volt or 1.8 volt. And they are running at a very less current, few milliamperes and maybe nanoamperes these days into the, or the microamperes inside the core of a controller. Now, these signals are not sufficient enough to actuate a valve or maybe to read a input coming from a input device, maybe the switch or a proximity switch, or it will be a push button. So what we need to do, we need to convert these signals. So digital input or digital or analog input signals, we have to convert them in a suitable voltage, the format that your controller CPU will understand. And these all functionalities done by the input module and the output module. Now, these input modules, they are mostly interfacing, as I was saying, 24 volt devices. So your proximity switches, for example, if we take an example of proximity switches, to sense an object, it will generate, after it senses the object proximity, it will generate a 24 volt as a signal. Now I have to interface this 24 volt with the PLC. But my PLC core is operating at a different voltage, very low voltage. So how the PLC will understand this signal? So that level conversion should happen. So the voltage level conversion should happen, and that is taken care of by the input module. Same is with the output modules. Once my PLC will generate logical high, a logic high signal, and then this high will be again 1.8 or 3.3 volt. But my relay will be operating, or my wall will be operating at 24 volt. So this level shifting or the signal conversion will happen in the output module. So there's an amplification of that voltage, so that I will be able to drive a motor, or it will be a solenoid from the output port. So that is the way the input output modules plays in a very important role over here. We'll discuss the input module first. So they are available in the different format, because most of the sensors and the input devices we are connecting to the input module. So either you will be having some kind of a push button over here, or it will be having a limit switch over here, or and then you will be having a common signal, that is the ground, that is connected over here, because all input signal should be given with reference to a ground voltage. That is what we call minus 24 volt over here. So now these input which are coming from the different devices, they will be interfaced with this input module over here. You are physically wiring them to the PLC, and then this input module have function of the shifting the voltage, that is the shifting voltage levels basically. Second function, it will be doing an AD conversion, that is analog to digital conversion. So that is the ADC part, that is analog to digital conversion. For example, instead of this push buttons, if I will be connecting a temperature sensor over here, it's a temperature sensor. If I interface, then I need to convert this input that is coming from the temperature sensor into a digital value that my controller can understand. So I will explain the ADC when we discuss the analog signal in detail. But if you try to understand basics of the digital and analog, most of the digital signals are in the form of a true or false. They are binary signals. So either the state is high or low, or it is true or false. All these signals are falling into the category of the digital signals. And when we talk about the analog signals, they are continuously varying signal. So if I'm talking about the temperature sensor, or if I'm talking about the pressure sensor, they will be reading the temperature which is varying over a range actually. So for example, if I want to read from 0 to 50 degrees centigrade or 100 degrees centigrade. So the temperature sensor will be producing a proportional voltage signal. So there is a voltage signal that is coming out of this sensor in response to the physical input that it will be sensing, or the physical parameter it will be sensing. So my voltage variation will be, if I have to write this, for example, that the temperature one, let's say that if I am using a temperature sensor, it will be reading 0 to 100 degrees centigrade. And then I will be getting 0 to 10 volt as an output from this. So that is how the mapping happens in the analog sensors. So the complete range of the temperature is 0 to 100 degrees centigrade, but my controller will be getting a 0 to 10 volt as a DC. And then now this is a continuously varying depending on what is the temperature outside. If it is a 50 degrees centigrade, you will be getting a 5 volt. If it is in a 30 degrees centigrade, you will be getting a 3 volt signal. So depending on the temperature variation, you will be getting a continuous variation in the voltage. That can't be read as a by individual bit here. So that need to be converted into the equivalent digital value, and that is done by this ADC. So then I will be using an ADC, that is analog to digital conversion. So if I will explain broadly the ADC unit, so what ADC will be doing, so there's an ADC unit sits over here, and you connected your temperature sensor over here. So you have connected your temperature sensor over here, and what it will be giving you. So if it is in a 3 volt coming from the temperature sensor, which is in response to the 30 degrees centigrade temperature, what I will be getting from the ADC will be a certain digital values actually. Depending on the resolution of the ADC, it means that how many bit resolution I will be converting or representing this 3 volt signal. Because my controller is digital, it will be only processing the data in the form of bits and bytes, and this temperature equivalent of the 3 volt signal has to be converted into the appropriate 8-bit value or the 10-bit value or 12-bit value, and that conversion happens with the help of this ADC. So then I will be reading this 8-bit value inside the controller and take an action according to that. So this is how the input modules are having the hardware inside it. So they are having level shifting, that is the level shifting of the voltage from the controller core voltage to the input voltage of the the input devices or the sensors that are connected to the PLC. Second function it has is basically to convert that into the digital format if there is an analog signal. So AD conversion will be there into the analog input module. So as I was mentioning, then you will be having a digital input module, or you will be having an analog input module. So all digital input will be taking the signal which will be directly coming to it, either 0 volt or 24 volt. So sorry, I will remove this dash because otherwise you will understand this will be range. No, it's not range. It is either 0 volt or 24 volt. And my analog inputs are coming from either 0 to 10 volt. They are coming within a range. So that is how all sort of inputs which are going to vary over a range of the voltage that are connected to the analog inputs. And the digital inputs are just an high-low signals, on-off signals, basically mostly captured from the switches connected to it. So either it's a push button or the proximity switch, or it will be a control switch. So these are the kind of signal that can be interfaced to the input module. Now, if you see here, this is a PLC rack here, where you will be having in a controller and then different IO modules over here. So if you see here, these are the IO modules that are connected over here. So as I was mentioning, we will be having these modules as an AI module or the DI modules and so on. Similarly, we will be having an output modules as. So in case of an input modules, either we will be having a different module for AI, and most of the time we'll have a different module for the analog inputs and different modules for the digital inputs. Most of the time in modular controllers, we'll have these. So this individual unit will be a kind of a module. So it will be an analog input module, or it could be a digital input modules. So if you can see that kind of inputs we are supposed to connect, we will be either connecting this kind of a toggle switch over here, which is either taking a state of on or off here. So this is a switch which will be producing a 24 volt DC. So where exactly we will be taking this, what type of module this will be, anyone? So what type of module we will be interfacing this switch with a 24 volt DC?
So digital module?
Yeah, it's a digital input, right? So you're right. So we will be interfacing it with a digital input module. Now, second module that you see, I will be monitoring a pressure here, and there's a pressure sensor which will be producing a current variation. So earlier we were discussing a 0 to 10 volt DC output from the sensor, which is input to the PLC. But here we will be having a pressure sensor which will be producing the same variation in the form of a current here. So 4 to 20 milliampere is the variation. And this is going to which type of module? Can anyone tell whether it's an DI or AI?
AI.
AI. Yeah, because pressure will be giving me a continuously varying signals, and this has to go to the analog input module. Good. And the same way, so this is the analog input with the current variation, and there's another module which is an analog input with a voltage variation. So it depends on the kind of sensors we will be using. So let me quickly explain where exactly we will be using a digital input, on whatever when I say digital means this digital one that is coming from the switches. But in case of an AI, that's analog input, we will be having a provision to either get the signal in terms of 4 to 20 milliampere, or we will be having a provision to get a signal in 0 to 10 volt. So these are the type of sensors available. Whenever we go for the selection, we need to understand when we have to opt for the analog input with a current as a variation, or we will be opting for an analog input with a voltage as a variation. You will find both the options available on the sensors, and that's an important parameter when we will go for the sensor selection. Now, why this is important? Let me quickly explain you. When the sensors are closely placed near the controller, it means that if I will be having a temperature sensor, but I will be wiring this temperature sensor near the controller only. It means that I will be placing this sensor which is placed near to the controller, so that the voltage drop in the lines or the voltage drop in the wires that are connecting the sensor with the controller is not significant. You understand that if I have, for example, 1 meter wire, so it may not be that significant. But if I will be mounting this temperature sensor, which is far away, maybe using a 5-meter distance or maybe the 10-meter distance. So then the sensor is quite far away from the controller, and the length of the wire that you will be using is also playing a very important role in the voltage drop. So that sensor on the site or the location will be producing a 3-volt signal, but your controller may be getting a 2.8 volt. So that is the difference, because 0.2 volt will be the drop in the wires that are connecting the sensor to the controller. It means that the actual parameter that is varying near the sensor is different. The value will be different than the controller will be understanding. So this drop is very critical when the sensing of that particular parameter is important, and then you are keeping the sensor far away from the controller, so that there's a significant drop in the wires that are connecting to it. So whenever the sensor is far away, we'll never go with the voltage as an output option from the sensor. We'll prefer to have the current output from the sensor. Now, when the current output is coming from the sensor, there is a circuit inside these analog input modules, which will convert them into the appropriate voltage. But this voltage conversion happens inside the controller module. So there is a resistance that will be used over here. And whenever the current flows into this resistance, there is an equivalent voltage drop, which this PLC will interpret, or this IO module will interpret. Now, this sensor, which is giving me the current, is responsible for maintaining a proportional current in the line. So now if the resistance of the wire increases, then the sensor will itself increase the voltage, so that the constant current will be maintained into that line. So this will give me the same voltage or the current at the controller level, in spite of, irrespective of the length of the wire, because depending on the external resistance, it will build up it will apply the voltage, so that it will make the same current flowing for whatever length you will be, whether it's a 1 meter length or whether it's a 3 meter, 5 meter, irrespective of the wire length and the drop in these wires. My sensor will be able to maintain the constant current in the line. And that way, if I will be placing the pressure sensor at a 10-meter distance, it is not going to make any difference to the understanding of the controller how much is the pressure at the site. So that is how the two type of sensors are available with the analog input option in the form of a current or it will be available in the form of a voltage output. We'll place the sensor close to the controller, then we'll go for the 0 to 10 volt DC. And if we are placing a sensor far away from the controller, then to compensate for the drop in the wires connecting the sensor to the controller, we will be using the current output sensors here. So I'm sure that this is fairly clear to you now. So both are analog inputs, but they are coming with the current sensing and the voltage sensing options here. And this one is a digital input as we discussed. So this is a digital input here. Now, this is what I was explaining. So when we talk about the digital input, that is the discrete inputs coming. It's a now we are talking about the digital modules and digital interface to the controller. So each bit will be storing the state of one input. So in this case, I am sure that you understand the digital to some extent. When we talk about the digital inputs, we will be talking about the, for example, 8-bit location inside the controller. It means that I will be having a memory register which will be of 8-bit. So you will be having basically the 8-bit memory locations inside the controller. So when we are interfacing digital input devices, for example, this push button or the toggle switch, then I will be only occupying 1-bit location. So this 1 bit is good enough. This location is good enough to store the state of this switch. So in that case, if the switch is on, I will be getting a 1 over here. If the switch is off, I will be getting 0 over here. Right. Now, when it comes to the analog, 1 bit will not be enough. For example, if I have to store the temperature of 30 degrees centigrade or 25 degrees centigrade, then I can't store in one single bit. That is what I was mentioning, that you will require multiple bit locations. So that is how it depends on the resolution of the analog to digital converter, that 3 volt is converted into 8-bit value, or it will be converted into the 10-bit value. So when I say 8-bit, what is the range of values that I can save? And if it is a 10-bit, what is the range of values that I can save? Or if it is a 12-bit, what is the range of values I can save? Can anyone tell? If I am using an 8-bit storage here, what is the range of values that I can store? What is the range of integer values? So most of them are integer values only. That is how we will be storing in the digital systems. So what is the range of those values that will be stored in the 8-bit register or 8-bit location? Anyone? So for example, this 8-bit register I have shown, so each will take a state of 0 or 1. And then if I have an 8 bits, how much is the maximum value that I can save or I can store here?
So 2 raised to power 8.
2 raised to power 8, right? So it's a 256 basically, 256, and we can say 0 to 255. So that I will be able to discretize the complete range of the voltages into 256 discrete values, right? That is how the 8-bit representation will happen. And when I will be having a 10-bit, then it's a 2 raised to power 10, that it's a 1024. Then it is taking 102, 1023. Same is with the 12-bit. So you will just see that. So 11-bit will be 2 into this, that is 2048, and then 12-bit will be 4096. So that is how 0 to 4095. So you will be discretizing the whole range of the voltage into discrete values. And this is how the binary value will be converted by the ADC. And then the controller will read that value. Is this clear? So if it is not clear, I will explain it again, but please understand how the analog will be interpreted or understood by the controller and how the digital value will be understood by the controller. Fine. So in that case, for storing, for example, the temperature value, then I need more than 1 bit. So it will be occupying the complete 1 byte, or it will be 2 bytes, that is 1 word location, that is 16-bit, depending on the controller resolution. So analog will be occupying a larger space in the memory than compared to the digital. So that is how 1 bit is used for digital input, and then we will be using either 8-bit or 16-bit to store an analog value. So this ADC will be doing that part. So discrete modules are available in this format. So you will be interfacing all the digital inputs to this module. And then your internally the controller will be reading that state with the help of a memory locations. So each input is mapped into one memory location. For example, if I am saying over here, so if I will be connecting one digital input over here, and so then I will be having internally the register over here. So you will be having 8-bit like this. So 0 to 7. So 1, 2, 3, 4, 5, 6, 7. So internally in the controller, you will have this kind of memory. And outside you will be having a screw terminals over here. So on most of the modules, you will find there are screw terminals. And these are 0, 1, 2, 3, 4, 5, 6, 7 like this. So if I'm connecting any of the input to this screw terminal, the state of this digital input is now reflecting inside that particular memory that is mapped. Either it will be 0 or 1. So input of digital input 0 is captured in the bit 0. Similarly, the input of bit 7 or the input terminal 7 is captured in the bit 7 here. That is either 0 to 1, 0 or 1. So that way 8-bit location inside the controller memory is sufficient enough to read the 8 inputs to the module over here. So you can interface 8 devices over here. And as many devices we are able to interface, we call them channel. So that is the terminology you need to understand. So this what we are calling is a channel. So in this case, we have 8 channels. So we will require the 8 memory location into the controller. So there's an 8-bit register that is being used. So each memory location we call this a registers. So registers are basically combination of the bits which are the physical devices which are storing the state of these bits. So 8-bit register means it's sufficient enough to store the 8 input state of the 8 inputs. So 8 sensors can be interfaced to this. That is how the digital module used to work. So if I am willing to store the state of 16 digital input, then I will be using a 16-bit register here. So it will be 16-bit register and we call it in a word, or this is called a byte like this, and single is a bit here. And that's a quick understanding of the terminology. But when it comes to the analog modules, so this kind of mapping will not work, because for each analog input, for example, I connected the temperature sensor over here. For each analog input, I will require a much larger space in the memory. So if it is an 8-bit analog input, then it will be occupying the complete 8-bit register. So this one register or one byte is completely used to store the state of just temperature only. The complete 8-bit is being used to store the value of the temperature. Same if the, for example, if I have pressure sensor over here, and this pressure sensor now I would like to store as a 10-bit resolution or 10-bit data, or it will be 12-bit data. So controllers internally may not be having a 10-bit register or 12-bit register. So registers are always in the multiple of 8-bit, because there's a byte and then there will be a word with a 16-bit and then there is a 32-bit location. So that way, if it is in a 10-bit, then the rest of the bits may not be utilized. So if it is a 16-bit registers, 10 bits will be utilized to store the analog value, and the remaining bits may not be used in that case. But my registers or the locations inside the controller will be either 16-bit or 8-bit or 32-bit or 24-bit that way, right? So depending on the resolution of the ADC, your memories bits are utilized inside the analog module. And that way controller will be reading those bits. So one analog input will require either 8-bit, 10-bit or 12-bit. That is one complete word inside the PLC memory, or it will be the 1 byte that is being used depending on the ADC resolution. Now let's talk about the output modules. We have seen that how the input will go and then we are converting into the equivalent 1-bit value, or it will be a 8-bit or 16-bit value. Now when it comes to the output that is to be produced, now this output is again of the type that you will be having a digital output or you will be having an analog output. Now, if I have to make the lamp on and off, or if I have to make a device on and off, then I will be connecting it to the digital output. So I will be just making the device on and off. But if I have to control something proportionally, it means that if I am opening a valve and I would like that valve will be 30% open, 40% open or 60% open, then I will be giving voltage input to the valve and then it will be opening accordingly. So this varying voltage output will also be required. And these outputs are basically known as analog output. Now what is happening in case of output module? PLC will be communicating a digital value only. So it will be communicating either 0 or 1 if it has to control the digital output over here. But if I have to generate a 0 to 10 volt output over here, because then it will be going to the valve to get open, then PLC will be giving either again 8-bit value over here or 10-bit value that controller will produce and which will be going inside it. So if you see here, the PLC data that is 8-bit or 10-bit is now get converted into digital to analog. So PLC will be communicating a digital inputs and then output that I am expecting is then an analog output over here. So then we will be using a device which is called as a digital to analog converter. So DAC. Earlier we have seen in the input module that's an ADC, that is analog to digital converter, because my input is coming in the form of voltage signal. I will be converting into the equivalent digital value, that is 8-bit, 10-bit or 12-bit value. That is how the analog to digital conversion happens, and that is required in the input modules. When we talk about the output modules, then the controller will be communicating the voltage, or that's a value, and which is converted into the appropriate voltage output to the terminal, and that is how the digital to analog conversion happens here. And we require a DAC module over here. So that is how the output modules will have a digital to analog converter and input modules will have analog to digital converter. But the phenomena remains same. Either you will be converting voltage to the bits or you will be converting bits to the voltage. That is how this conversion happens here. And then accordingly, you will be controlling the devices here. Like this, if we have these 4 different type of output devices, I would like to control a valve which is proportionally open and with the range of the values, that is 0 to 10 volt DC. So 0 will be keeping it fully closed, 0% opening, and 10 volt DC will be making it 100% open, that's fully open. And then in between also you will just pass on that voltage and the valve will be opened accordingly. Then other than that, we will be having a fan that you will be running at a different speed. So you will be having that fan operated with this analog output module. But if I want to make just light on and off, most of the time in machines, you will find that there's are indicators, there's a light that is going to make on and off. So controller will take a decision to make that light on and off, and that kind of light will be made on with the help of 24 volt supply to this light, or it will be just giving 0 volt to make it off. So that way this is now interfaced with the digital output, and this is all interfaced with the analog output like this. Right. Fan may be of different type. Fan may be without varying speed. They may be also be operating as an on and off. That is also possible. So if I'm not writing that the speed of the fan will be varied here, then it will be just on and off. So then I will be just using a digital output module here. So you need to be careful in that what type of module that you will be using over here. And this is only the analog output that will be generating. Right. So that's a way the output modules will be utilized. And I will be covering a little bit about the PLC programming as we go along in the class, but you will be doing lab on that. So certainly maybe it's a mix of that. You will be learning in lecture and then you will be doing the experiment, or initially you will learn it experimentally, then I will be explaining that in the class. So initial classes now we will be focusing on understanding the controller programming, and that is how your first lab is scheduled today, and the meeting link has already been shared with you. And the TA has also shared some of the softwares to be installed. So if you are able to do it in your systems, that will help you in conducting the lab or performing in the lab. Otherwise, TAs will help you how to use those softwares. So we will be learning how to program a PLC, and then you will learn the basic instructions. I have just explained you the interface, the physical interface to the controller, but how to connect them through the logic, that you will learn in the lab today. I think that's all for today's class. I will stop over here. If you have any doubt, you please let me know.